Hello everyone, you Dr. Zia Tahir here. This video tutorial is solution to problem 8.30b from chapter 8 continuous system of mechanical vibration by 6th edition by S.S. Rao. So that is 8.30b part from mechanical vibration by S.S. Rao. So problem description: compute first three natural frequencies and corresponding mode shapes of the transverse vibration of uniform beam of rectangular cross section. Width or breadth is 100 millimeter, depth is 300 millimeter, length is 2 meter. Modulus of elasticity is 20.5 into 10 to the raised power 10 Newton per meter square. Density is 7.83 into 10 to the raised power 3 kilogram per meter cube. For the beam when both ends are built in. So this is fixed end beam. So objective is to find first three natural frequencies and to plot first three mode shapes. And equations for them are natural frequency. This is equation 8.93 of chapter 8 of the book Mechanical Vibration. So omega is equal to beta EI over rho A or beta L squared EI rho AL. So E is there, I is the second moment of area, A is the area. So here BL is the solution of frequency equation. And when the both ends are fixed, so frequency equation is cos beta and L in cos hyperbolic beta and L is equal to 1. So need to solve this equation and then for first three roots and then need to substitute those roots here to get natural frequency. And then the mode shapes, so Wn is the mode shape and that is expression for mode shape, and it Cn here is 1 and that alpha n is that is expression for alpha n. So to, to calculate Wn, beta n is required, so which is computed from here. So then I'm going to solve this in MATLAB, and in MATLAB I'm going to use VPA solve function. So it solve equation, so it will be used to solve that equation, frequency equation, and the double, this is also used for solving the equation, and then the plot. So plot is to create 2D plot in MATLAB. So the first step is to solve frequency equation. This frequency equation is taken from figure 8.15 of chapter 8 for both fixed being, and the frequency equation is cos beta n L times by cos hyperbolic beta n L is equal to 1. So to solve that frequency equation, I have already recorded two videos in mechanical vibration solution. So that is example 8.17, solution of frequency equation for single root, and then solution of frequency equation for 5 roots. So MATLAB script to solve equation to find roots. So that is explained in this example 8.18 video, and I'm going to use the script which is used there. So that is a MATLAB. I'm using the layout as a default layout of it, and I'm going to start a new live script. So for live script, you have two options. Either you can output on write or output inline. I'm using output inline. So that is here, double percentage sign for title, and that is problem 8 point natural frequency and mode shape of fixed beam. So I am going to maximize it. So it's being maximized here. So the first one is I need to solve frequency equation. So that is solve frequency equation and put enter. So it is now a heading here. for frequency equation. So to solve frequency equation, I'm going to use MATLAB symbolic solve function. So VPA solve is the next. So it evaluates values for particular equation. And here is it a VPA. First need to write equation, and that equation need to write, and then variable here is BL, and then need to give initial parameter. So range to search the values. So I am looking for the first three modes. So I'm going to now write a small script to calculate beta L or to solve frequency equation. So that's CLC to clear screen and then clear workspace. So then I have started a SYMS, that is a symbolic system. BL is the variable, and then equation is cos beta L into cos hyperbolic beta L is equal to 1. And then, so here is a VPA solve equation, that is equation for variable BL, and I and J. I'm trying to find the values between I and J. So what is I here? So I have defined here like 1 to 10, and J is the next value of it. So for loop, I have created that BL is equal to 0. That is an empty metric, and then whatever is the VPA value, I'm going to convert into double, and then the cumulative BLI will be, so it fill all the values, and then I'm going to display that BLI. So I have just executed the function, and it gave me three values. So you can see it. So the first value is 4.73, the second one is 7.852, and the third one is 10.9956. So these values are here. So for fixed beam, the first value is 4.73. So then there's the first, second is 7.8, and the third one is 10.99. So these are the first three values I have computed. So in this way, you can compute that values of beta L, and now I am going to use these three values to find frequency. So now the next step is to achieve first objective, to find first three natural frequencies, and that's a formula. I'm going to use that omega is equal to BL EI rho AL. So first I need to uh, in MATLAB I need to input beam parameters and then compute A and I. So I am going to add next heading as beam properties, and then I'll add all beam properties here. So beam properties length as 2 meter, width as 100 millimeter, depth as 300 millimeter, E 20.5 into 10 to the raised by 10, rho as 7.83 into 10 to the raised by 3. Then area is B times D, and I is equal to B times BD cubed over 12. So these are the beam properties I have added. So the next one, I'm going to add a heading to find natural frequency. So that is the next heading to find natural frequency. And now I am going to input that formula of natural frequency. So that is the natural frequency omega n is equal to BLI square root EI rho AL raised by 4, and then natural frequency in hertz. So that are the natural frequency in hertz. So I can run that one. Okay, so once it is being run, so these are the three values of natural frequencies. So that is the solution manual for 8.30, and for fixed beam, first natural frequency is 202479, the third one 6830, third is 13393, and these are the values here. So 10 to raise by 4 it is. So these are the values 2479, then 6832, and the third one is 133.94. So these are the natural frequencies calculated, and they are same as up from the solution manual. So the next step is to achieve the second objective, to plot first three mode shapes. So for the first three mode shapes, here is an expression. So the values which you got here from frequency equation beta L. So from there, need to get beta and then need to substitute that beta in this equation. So first A and need to calculate. So I am going to write a function for this one in MATLAB. So the next heading I'm adding here as mode shapes. And the mode shape, I need to first write a function. So remember, if you have to use a function within the script, so that should go right at the bottom. So function name is mode shape, and I'm giving it BL, DX, and L. So DX, L is the total length, and DX is like to plot it. So X is from 0 to L with a step size of DX. So, and then B is BL over L. So that BL is here we have already calculated. And then I have first find alpha, and alpha is written as A. And then for simplicity, I cosine of BL I use as C, cosine of sine of BL as S, cosine of hyperbolic BL as CH, and then sine of sine hyperbolic as SH, and then that is the alpha, which is sine hyperbolic minus sine over cosine hyperbolic, cosine minus cosine hyperbolic. So that is sine hyperbolic minus sine over cosine minus cosine hyperbolic of BL. So that alpha I calculated there, and then I need to find that C. So C is again, so because I have used those values to calculate A, so that same variable name I'm giving it as C is cos bx, and similarly S is sine b into x, cos hyperbolic b into x, and sine, and then I got W. So it is sine hyperbolic minus sine plus A times by cosine hyperbolic minus C. So that is the function because I have to use it for the three times. So that's why I have written a function for that. So that is a function. So now I am going to execute that function for three values of BL. So first I'm going to draw base state, and then I'm going to plot uh, all other shapes. So now for the base state, so I'm going to set here dx as zero point 0.01. So x is from 0 to L with an interval of 0.01. And then I have used that W0 that is uh, like the base state. And I just, because for the base state, so there will be no uh, deformation or displacement. So I set that displacement as 0. So plot x, and then that is the mode shape for, or that is the uh, W, which is normal function, and then uh, black color with dash line. So I set hold on, and then I set the labels for it. So this will compute the base state. So that is the base state of B. So I'm going to clear that. Uh, so here, if you right click, and then you can clear this output. So next I'm going to get the script for first mode. So that is the first mode. So for the first mode, I am going to use that's the first value of BLI. So the first value of BLI is 4.73, and then I'm giving it that mode shape function. So output as W1. So BL is the first value, first root of that frequency equation. DX defined as 001, and L is already defined as 2. So that is for the first mode, and I'm going to repeat it for second and third mode. So for second mode, I have used second root, and then I computed that using mod shape function here, W2, and then for the third mode, again is the same one. So BL3, which is that is 10.96 value, and then I'll compute that W3 using all that value, and then I'm going to add the legend, base state, first mode, second mode, and third mode, and I'm going to plot it. So I'm going to run that function. So when I'm going to run that function, so that is mode shapes, these three mode shapes. So I am open figure in a new window, and then I here using view plot browser, so I can plot that. So that is the base state, then that is the first mode, that is the first mode, then that is the second mode, and then that is the third mode. So that first three modes are plotted. So now that second objective is being achieved. So this is, and then here I can minimize it, and all these parameters are here. I can just, so this is uh, how to plot natural frequencies and mod when both ends are fixed or built in. And here in the solution manual, the approximate figure is also given there. So that is for the fix being approximate figure. I hope you find this video helpful. Thank you very much for watching.